Okay, so now you may have noticed that there was not a written assignment this week. So I mean, I'm not that mean. So there's a midterm on Monday, so I'm not going to make you do some extra stuff for that. So you can basically prepare for that. There's just the computer assignment that's due business today that you've been working on for a while, and especially for the Python folk, there was some glitches in terms of my getting a little whiplash and going from Java to Python and back and forth. So it's like, well, I don't expect any sympathy for this, but if you know, it's hard enough just kind of getting stuff to work in one language, but then kind of doing it in two, and of course that that gives me also an extra appreciation for those of you for whom English is a second language, because it's like that must be even more challenging. You know, I know that I mean, all of the English that I've heard from the second language speakers is excellent. So it's not that, but there must be some kind of weird context switch that goes on in your brain if you switch from one language to another. Anyway, so that's what I've been experiencing a little bit. And part of it is just sort of a 1.0 thing, just for those of you. This is the first time I'm actually running the course with that Java, with that Python implementation. So and it's not my native language. It's not my favorite language, but there it is. With respect to that, there's a link in the lessons to a couple of handouts. One is the suggested solution to the sample midterm, just to kind of give you an idea of that. And a second document, which is just sort of a list of topics in terms of what I think we've covered. There's also, there's now in the topics document, there's a lot of stuff on SimKit and also the Python one. That's, don't spend a lot of time on that. I mean, that's something where, if you've been doing the computer assignments, then there's certain things that you just should have been able to absorb. So for example, on the Java side, if if there's an event, then that translates into a method called do the event. Whereas in Python, it translates into a method that just has a lowercase. So that, and just some of the, in other words, there are just a handful of things there. And that's not my, I mean, it's something that's in there because we've covered it. And when it comes to simulation models, the emphasis here has been on understanding how discrete event works, the event list and all that. Understanding how time varying statistics work and how they're different from the tally ones. And most importantly, the idea of how events move from one event to the next and not according to some fixed time step type of situation. And then, we spend a lot of time creating event graph models. So the one question that I will guarantee is going to be on the midterm is going to be a formulation-like question. And now, as you've seen, formulation questions can be tricky. And in a 1 hour exam, if I ask a question that would take you a couple of hours to just kind of figure out, then that doesn't give me much information about how you've kind of absorbed this. So the formulation question will be a relatively small one. I mean, but it won't be trivial, but it won't be a big one like some of the models we're going to be talking about, especially the one I'm going to talk about today and the model I'm going to talk about tomorrow, which is going to be the biggest one that we've done so far. Okay, so first, what I want to do is yesterday, I was we were going into some specifics about how to create event graph subcomponents, and one of the key things for that was just when we override an event or we create an event in a subcomponent, what is it that we want to do with it? And there are basically three options. One is we want to augment that superclass event. That's what we've done mostly in our arrival process variants, where in the super event graph, the arrival process is one that actually schedules all of the arrivals and keeps them coming. But if we want to do something a little different, like say create a part or create a customer, then we do that in a subcomponent, we still want those arrival things in the super component to keep coming. And so that's what it's meant by augmented. In other words, I want the arrival event to do something new, but I also want it to do something old. Whereas the second one, where you have a kind of a dark, a heavier border on this, is where there's something going on in the super component event, and I don't want any part of that because it's not why I want to do something a little different. And that's some of what we're looking at here. So an example of that was this batch arrival thing. So we had our multiple server queue, which just had arrivals coming one at a time. Then there was this idea of, okay, batch arrivals. So they show up in a batch. And then we had an event graph that looked almost like our original one, but it just added this extra little thing. That was just, so that's when you're adding something, you're basically just sort of tweaking something, then the virtue of laziness says consider doing it the lazy way. So while we could implement this, kind of from scratch like this, it's also beneficial, again, applying laziness, to just say, okay, let's use everything we have already. And basically, what's different here? What's different is that the arrival event in the multiple server queue component only adds one to the queue, whereas we want to add the batch size to the queue. So that's completely different. And so in that case, we don't want the arrival event in the superclass. But what we wanted, the other thing we need, so one thing is we need to change the state transition. And usually when you've changed the state transition for a state variable, then usually you want to kind of override the whole thing. But for the start service event, though, it's like the start service event, again, in the multiple server queue that doesn't have this, it just schedules one end of service for that, but we want to schedule multiple ones. So we want the start service event in the super component, but we want to kind of keep scheduling those as long as we have an available server and somebody in the queue. So, and the reason for both of these conditions is that we don't know if we're going to run out of servers or customers. In other words, if we had 5 in the queue and 2 servers, then we would take 2 of the customers and leave 3 in the queue. Whereas if we had 5 servers and 2 customers, we would run out of customers first. So that's what this condition does. And then just for the Python folk, and again, this is in Java, the Boolean and is the double ampersand. In Python, it's the word and. Why did they do it that way? I have no idea. But ever since the dawn of time, the double ampersand has been the logical and, but okay, but whatever. All right, so what I want to do is I want to show how should I say, it's like the advantage of having what I consider to be a very straightforward way of taking an event graph and turning it into a running program is that, you know, the acid test comes where, does this actually work? This is the thing. And I have to say, how should I say? It's like, sometimes when you look at things just on paper, it looks like they should work. But then when you go to implement it, it turns out there was something that you forgot and that it didn't quite work. All right, so the acid test is, does this work? And so if you pull the class code, you will see that I've done it a couple ways. I think I'm just going to talk about the one way. So I'm going to implement that. So in the there's a class called Simple Batch Server. There's a Simple Batch Server 2, which does one that's a little bit later. But I'm just going to talk about this one because so again, I mean, think of the programmer virtue of laziness says that the lazier you are, then the more likely it is that your code will actually work. So what does laziness mean? Laziness means that we have our simple server component that we've already hopefully implemented, debugged. We have a component that's working. So we're going to kind of keep that. So instead of reinventing that wheel, we're just going to add the piece that we want. And the piece that we want, now there's overhead that we have to do, which is all in the constructors. But that, you know, this isn't code really, you know, sort of setting things in constructors. I mean, that's not programming. That's just kind of bookkeeping. But what do we need? We need a batch generator, something to generate the batch files. And then we need to do something to override our arrival. Yeah, let me share my whole screen so we can kind of flip back between these. So, okay, so this is all we need to do. So we need to just implement these two and get a model which does something brand new. Okay, so here's our arrival. And now we have a batch generator. We're going to generate it in. So I'm going to circle back and talk about what that is. In the Python version, again, because there's no concept of interfaces or things like or overloading and things like that, it's a little bit different. There is a version in the Python one, so you can, if you want to pull that up and do a pull on what's going on there, you can kind of follow along. I'm just going to cover the Java version here. So we generate our batch from this thing, which is a discrete random variate. So far we've been using random variates. What do you suppose a discrete random variate is? It's discrete. In other words, like discrete distributions are things like Poisson, binomial, Bernoulli, geometric. And in fact, the one we're going to use here is one where you simply, when we get to the implementation, we specify the possible values and we specify what the frequencies of those are, and it'll generate those based on that. So in other words, you can specify an arbitrary values and arbitrary frequencies or probabilities, and it'll generate from that. And that's how I'll implement it. And part of the reason is that distributions like binomial and Poisson have a non-zero probability of giving you a zero, which, you know, it's like you know, in a sense, like, you know, somebody a batch shows up, but there's nobody in the batch. So it's kind of what? Anyway. Okay, so we're implementing this. So what is this? This is incrementing Q by the size of the batch. So again, the old number in Q, we set the Q to the incremented by the batch and fire our property change. And then because we've completely overridden the superclass arrival, we need to schedule our start service for this. And this now the extra, if by some chance there was nobody in the queue and a batch size of 0 just happened to show up, then that's why this extra test is there. But all we're doing is we're just implementing this. The one little additional thing I'm doing here is I'm kind of pretending that that batch is actually a state variable here. I mean, I could have added that as a state variable and done the whole thing. You'll see why I was doing that there. And that's really all we need. So if we to run this, run simple batch server. Okay, so I was choosing the same parameters as we had for the other. And here's how we, here's an example of a discrete probability distribution. It's called discrete integer. It also has the standard ones, you know, like I said, Poisson, binomial, Bernoulli, geometric. Those are sort of the main standard ones, but here's one where we give it an array of values. Here, this 1, 2, 3, 4, and then we give it an array of frequencies. And then our random variate factory has a method called, which is probably more verbose than it needed to do, but it's instead of get instance, it's get discrete random variate instance, and I give it the name. Now for this, I need to give it the name. I need to give the array of values and the array of frequencies. And what that does, we can sort of see what that looks like here is that it, notice that the frequencies, when I say frequencies, they're not probabilities. So if I give it, I say these are the relative frequencies of each of these different values. So what does it do under the hood? Well, what would you do? If I gave you a bunch of frequencies and I said, turn these into probabilities. Yeah, add them all up to, well, divide by the sum, whatever the sum is. In this case, the sum happens to be 100, but yeah, whatever the sum happens to be. And then as you can kind of see, when you print it, it kind of comes out like this. Here are the probabilities, and here's the cumulative probability, because when you generate, just we'll talk about this when we get to random variate generation, but the cumulative distribution function is more useful than the probabilities themselves, as it turns out. Anyway, okay, so we have that. Now in this, now notice that if we run it with our, originally we had like 2 servers. If you run it with 2 servers, then you get, well, we see that the average number in Q is something like 31,000 or whatever. You know, why? Because there aren't enough servers. That's why. Turned out that at the minimum, you needed like 4 servers to at least have something. It was still not very good. These aren't very good metrics, but you know, have the same number of, roughly the same number of arrivals, but now notice that we have a whole bunch more served. And this, you know, average number in Q32, that's the, you know, that's a terrible, you know, that's a terrible one. But, you know, okay, but at least it's not like 30-some thousand, you know, 30,000. I mean, that if you tried to run a system like that, I mean, you would have, that would be like the restaurant nobody goes to anymore because it's too crowded. So, you know, and then, so basically, if we added a 5th server, then you actually get metrics that are kind of reasonable, you know, so average number back to that, you know, so, you know, those are the, but as you can probably hopefully tell, it's like when you're in this situation, The levers that you typically can pull are just how many servers do you have and how fast you can make them, as we talked about the other day. What else did I want to? Oh, yeah, no. So how did I get the number served? If I just counted the number of arrivals, the problem is that the number of each arrival had more than one. So what I did was, remember, I fired a property change for the batch. So for each batch said, this is how many in the batch. And I tallied that up. So in fact, I could tell you what the average is. I actually know what the average is because I know what the distribution is. But how many did I actually get to get served? Well, let's see, that's actually not quite. I think oh yeah, I was just telling the arrivals, but that was actually the number of that was actually the number of arrivals, as it turns out. But and it was like 129, something like that. But the main point is that when we do a subclass like this, then that's one way to do it. Now, well, I'll just kind of point to what the other one was. Was actually sort of similar. Yeah, no, I do want to get to the model for today, but yeah, so there are a number of different approaches one can take to this. There's not just one way of doing it. Typically in these, there's more than one way to correctly model a situation. There are infinitely many more ways to incorrectly model it. So just and remember the dictum that all models are wrong. So all models are still wrong. Some models are more wrong than others. So you know, so a model that doesn't really do what, you know, so for example, the multiple server queue model that just had one arrival was the wrong model for a situation where more than one customer shows up. I mean, it's the correct model for situations where one customer shows up at a time. It's the incorrect model for dealing with batches. So there's that level of incorrectness. For a given requirement of how a model is supposed to be running, there are, you know, typically a number of different ways of capturing that. So there were several different ways of capturing the batch arrivals. I showed you one. There, you know, we talked about a couple more yesterday, and I've implemented a couple of them for your perusal. Okay. So now with that, today's fun is, okay, not with that, it is with this. Let's see, so can everybody see this? Okay, so a while back, we did a simple model of that represented a finite calling population. And if you remember, I kind of harangued about the infinite calling population versus a finite one. It is an important distinction because typically for kind of customers coming from the outside, it's you know, so for example, like if you're modeling a retail facility, even on a place that's relatively not densely populated, like the peninsula here, there's still maybe a little over 100,000 people on the peninsula. So like if you're a retail establishment and you have like 20 people in there, the arrival rate is not seriously affected. On the other hand, if you have a finite number of machines that are failing, then that's a very different thing. Or maybe you were modeling, oh, I don't know, maintenance on aircraft carriers. Arrival process is not a very good one for that. Is that pretty clear? Because you only have what 11 of those, so it's like, and if like if like 3 of them are in maintenance, then the rate at which stuff is kind of being dealt with is a bit different. Okay, so we in our most basic model, we had a situation where we had an operator on a machine, they're working on the machine, and then if the machine fails, the operator is also the repair person. So the machines didn't have to queue up for repair people. And then there was usually I ask this as an assignment, but I think I forgot this time. So now imagine that isn't the case. Imagine there are different repair people for the machine. So when a machine fails, then you have to queue up for a finite number of repair people. Okay, can you envision that? Hopefully, okay. And that's the next most interesting model for that. But now we're saying, well, okay, what is the impact of that on the throughput of our jobs? In other words, if you're running this place, you don't really care about the machines except as they impact your ability to process the jobs. In other words, your customer, as it were, doesn't care about the machines, they care about the jobs that are being processed. I mean, just as like if you're a maintenance facility and you're doing maintenance on a piece of equipment, and the resources that you have to do that maintenance are failing, or you're having to deal with that. The customer for whom you're doing the maintenance on doesn't give a crap about any of that. They just want to know, they want their stuff, right? So the model in which the machines were the customers and the repair people were the servers doesn't capture that. And so we want to capture that. So now we have an interesting situation. So we have repair people who are our servers. We have machines which play a dual role. The machines are both a server with respect to jobs, but a customer with respect to repair people. Okay, so what happens when a machine fails? Just kind of thinking of metal cutting type of things. Often, when a machine fails, it just destroys the job. So the context of this is something like where, let's say you've contracted to produce a certain number of widgets. These widgets have to be processed on these machines, and then the problem is that when the machine fails, it just destroys the piece you were working on. That's the situation in many cases. And so that's the lost job. So basically when a machine fails, you lose the job, you lose it. On the other hand, there are situations where when the machine may fail, but this job is still viable. And there, the interesting situation is, okay, now how do you handle that? So let's say I have a piece, let's say it requires an hour worth of work on this or some similar machine, and I work on it for a half hour and then the machine fails. And okay, so I've done half the work on this thing, and so I only have half more to go. So what do how do you capture that? That's what the second model is going to do. Okay. So so we're going to have jobs that kind of show up for this. And this should look very familiar, so we have an arrival process, and our arrival is going to say, okay, for our arrival, we're going to create a new job and then schedule an arrival for that. That's very familiar. Now, the thing is that to start capturing this, here's the other nuance. In our original model, the time to failure was based on clock time. So if I had a machine and I said it's going to fail in a certain amount of time, I did have, wasn't there a homework assignment about this? Yeah, okay, yeah. So now when there was a failure, I'm sorry, when you repaired a machine, you scheduled a failure with a certain failure time. With that was a calendar time. Okay, and for some situations, that's something reasonable. However, in many other situations, in many other situations, that isn't a reasonable assumption. In other words, what causes a machine to fail? Wear and tear, stuff going on, whatever. But if a machine is just sort of sitting there, is it failing at the same rate as when it's like working? I mean, like if you're, I don't know, if you're looking at the bit on a drill press, is the bit getting worn out at the same rate when it's just sitting on, and not doing anything, or when it's cutting? So, okay, so that isn't, so you see the little subtle issue with scheduling failures based on calendar time. So we want to fix that. So we want to schedule our failures based only on the time that we're processing. So when a machine is idle, it's not failing. But when a machine's processing, it's basically it's like our Reneg model. If you kind of go back to that, internally there was this kind of time bomb that each customer had, and if it went off, they left. Similarly, we have a machine has this time to failure, which is processing time to failure, and we want to capture that. And the way to capture that, or a way to capture that, is with an entity on the machine. And so we have an attribute that says that's the remaining time to failure, meaning the remaining processing time to failure. And we need a setter and a getter, because every time we repair the machine, we're going to have to generate a new one for that. But then in addition to that, we want to credit the work. And one of the nice things about the way that entities work is that if we've stamped our time and we've let's say we have 5 hours left until processing till we fail. And the thing is, the model knows that, but the people working it don't know that. But so let's say I have 5 hours to fail, and okay, so a job comes in, I work on the job for an hour, and after finishing that, I now have 4 hours of processing time to failure. On the other hand, supposing I have 30 minutes of time to failure, and a job that requires an hour comes in. So now, what's going to happen? Well, I'm going to work on it for a half hour and then fail. Okay, so how can we capture that? Well, I can get that time from this entity here. And let's see. Okay, so I think for this, I'm not a slightly better model. Well, again, just remember iterative. So with the first cut, I'm going to actually generate both the repair times and the processing times, and and I also need the forgot this. I need the times to failure as well. Okay, so I'm going to have an array of all the machine entities, and this is similar to what we were doing with our servers in the other model. Now, for the repair people, I'm going to just go back to sort of the count. So I'm going to have the number of repair people and just a single count of those. Although, again, we could We could do that with the set, but let's keep it simple for the first iteration. So I need repair times, I need processing times, and I also need times to failure, which I forgot to put on the slide. And so I'm gonna have a queue of waiting jobs. I'm gonna have a set of all the available machines because they're working as servers for the jobs, but then I'm gonna have another queue of failed machines. So unlike our simpler model where we were just counting the number of failed machines, I'm going to have a queue of those things. And the advantage of that is that as you saw in that problem, if I'm just counting the total number of failed machines, then the conditions get a little bit tricky, just as you saw. Okay, so let's see what that looks like here. So again, always start with run. And so we have our containers, and the typical approach in this, kind of using the event graph for loop to initialize things, is to kind of clear them out first, set our scalar state variables, but then use our init, as it were. And so what we're going to do is we're going to first, for each init, again, this is iterating over that array of these machine entities. First, we're going to set its time to failure by our T sub f, our failure times, and then we're going to simply add it to our available machines. So this is the same as what we were doing with our server entities in the previous model. In the code, it doesn't matter because you would still have a reference to it. In other words, I can put it on if I have an object, I can put it on a container, but if I still have a reference to it, I can call a method on it, which is all you're doing here. Is that? How does init know what actually that's not bad? Well, you had the index and you had the array. Okay, the question is, how does the init know what S is? And that's the great question. Okay, S is the state variable of available machines, so you have access to that. All is the array, and I is the index that you've passed in. Yes. Yeah, all was the array. Yeah. But these are all the things that you should be asking. Exactly. Okay. So, and now we've done this a number of times. So our arrival is going to have a job as its argument. We're going to stamp its time and then add it to our queue. And then if again, this top piece is almost identical to what we had when we were using server as entities. That's partly why that model was there. So our start processing event, we're going to pop off the job. We're going to pop off a machine. And then for some reason, I'm stamping that. The reason for stamping the time is that this machine could possibly go on a queue, but we're going to stamp it again there. This may not be necessary. Okay, so now let's see what happens here. When we start processing a part, we don't, or at least we don't know, but the model does. Is it going to fail first, or is it going to finish the part first? And so the end processing event needs a condition, and the condition is that our service time that we've generated is that less than the machine's remaining time to failure. And if it is, then that means that we can finish processing. We can actually finish it before it fails. On the other hand, if the amount of required time that this job has is greater than the time to failure, that means that we are going to fail first. And the delay on here, which I forgot to put, is going to be the time to failure. So now, if we actually do finish processing, we do need to credit the work. In other words, we've credited the work. So the reason we stamped the time here is on the machine. So we do need this. We stamped the time, and so the elapsed time between when we started processing and when we finished processing, we've spent that amount of time working, and so our time to failure is that much sooner. In other words, the time to failure is just how much time we had left minus the elapsed time. That's why that was. On the other hand, if we have a failure, then now we're this bottom piece is we're in another multiple server queue here. So we add it to our now we stamp the time because it's now later than when we stamped it earlier, and we add it to the repair queue. And then if there's an available repair person, then we can start repair, and we should probably have a high priority on this. And then when we start repair, we pop it off the repair queue, take away one of our repair people, and then schedule an end repair, passing the machine, because we want to know which machine actually finished repair. And when that happens, we've now finished the repair, so we have an available machine, and we need to set a new time to failure. So we set our time to failure based on a new generated value. And then, because we now have we've added in its role as the server, the machine now has could possibly process a job. So if there's a job waiting, like if all the machines have failed and now we have one that's repaired and there are jobs waiting, then we need to say if there's a job waiting in the queue, then we can schedule another start processing. And why does this pass on? That shouldn't be there. Okay, so and then yes. Oh, that timestamp is for adding to the queue. Do we really need that? Remember that the comparable implementation in entities has to do with the timestamp. In other words, those with a smaller timestamp go first. Yeah. I said, yeah. Stamping the time like this ensures a first in, first out. And that's a way to do it. As you may imagine, we might imagine different priorities, which is something that we could do. And that's why, how should I say, like if we implemented this strictly as a first in, first out, then we wouldn't necessarily have to do that. Actually, what I've kind of landed on is the implementation as sorted sets using the default comparator. And the reason for that is that sometimes we want to override that and have a different criterion. In other words, we might have, well, like one of the standard sort of job shop like things is that if we process parts, if we have different jobs that have different service time requirements, if we process those not in first out, but in the shortest process called SPT, or shortest processing time first, regardless of when they came in, then it turns out that that has if we want to optimize our throughput, then that's kind of the way to do it. This isn't a class in that, so we don't have to delve deeply into that. But because those things come up, and actually in the models that I'm writing for NAVSUP, that actually has come up. So there was a when it had to do with procurements, different procurements have different amounts of administrative lead time that they have, and so they want in order to make a procurement, then you need what's called obligation authority, and if you don't have enough obligation authority, then you can't make the procurement. And so if needs of procurements kind of stack up, basically in a queue. And so how do you process those? So the first versions of the model were doing first in, first out. But they said, well, wait a minute. We want the ones, they actually want the ones with the longest administrative lead times to go first. Okay, so first in, first out isn't going to work for that. So we need to implement it. So my point is that that's not just an academic exercise, it's something that actually comes up. Okay, so now the thing is, one of the sort of a little subtlety here that was that I want to point out here. Notice that when we pop the job off the queue, it just kind of went away. So here, a critique of this model is, since we're kind of quote losing the jobs, I would want to get some more information out of this model, like what percentage of jobs are we losing because of machine failures, and for those jobs that finish processing, what about their times? So those metrics are not captured by this particular model. We can capture the second one simply by passing the job to the end processing, as we were doing in the previous model. Didn't do it here, but that's, that was just sort of a design choice. But the thing about iterative modeling is that, even if we're, you kind of look at it and say, well, okay, does this meet all of the needs that I have? And if it doesn't, then fix it so that it does. Okay, so this is not a perfect model, but it's as you can see, it's getting a little complicated. Now, what gets even more complicated is if we don't just kind of there, the job was destroyed. That's why I didn't care about it. But what if what if the job does not get destroyed, but we want to credit the work? So, and this is a similar type of logic as we had in the times to failure for the machines. In other words, the job was processing for a certain amount of time, and if the machine failed, we want to credit the job for that work. And so now we want to move the processing times to the job, because we want to give each job, and I'll call it the remaining time, because that's the amount of work that has to be done on the job to finish it. And now we don't need to set anything because it's just in there, but we want to get the remaining time and we want to credit the work. And we'll be crediting the work in a similar way by stamping the time and using the elapsed time. So again, now the job arrivals are going to have we've moved our processing times into the job arrival process. And now it gets a little bit more complicated, but okay, the init is basically the same as before. Oops. Okay, but now, and in fact, as we can see, we still, when we end our processing, we're still crediting the work on the machine. This model also isn't kind of doing right by the jobs either, but now our failure event has both the machine and the job, because this is the failure of a machine that's processing this job. And so how do we know which one it is? We know which one it is because we popped it off the queue here in the start processing event. And now when there's a failure, we credit our job with the amount of time, and that's why this should have we should have stamped it back here. Okay, but now, and the logic here for the repair is exactly the same as before, but we now have a job which has a certain amount of remaining time. And if there's another machine, what we can do is we can put it on that machine and start processing that. So if there's an available machine, that is, if the container of machines is not empty, we can then schedule another start processing. And notice that we've put the job back in the queue. So now if there were other jobs in the queue, then there wouldn't be an available machine. So this would be false. But if there weren't any other ones in the queue, then when we popped it off here, it would be the only one to pop off. So like what's it, the Russian Uber driver named pick up and drop off. Okay. All right, so those models, so okay, and then now tomorrow there's going to be an even more complicated model. So I think I'd better make sure I got that one correct. So if there are no questions, I will see you tomorrow.
I do have a question.
Yes.
It's going back to the computer assignment that's due today, though. I'm running into an issue with the default constructor for transfer line component. Total number of machines ends up being null. I think I'm just missing something fundamental there.
Okay, can you
I'm sorry. Your mic is cutting out.
Okay, tell you what, can you come back on this Zoom in like about 5 minutes? I'll go to my office and I can answer the.
Yes, sir. No problem.
Yeah. Expecting that. Just need to